Have you ever looked up at the night sky and felt a sense of wonder? A feeling of connection to the vast, silent cosmos stretching out above you? We are, all of us, explorers on a journey through space and time. But some journeys are not just across the stars, but deep within the human mind. This is the story of such a journey, undertaken by a solitary boy who dared to ask questions that no one had thought to ask before. A boy who would, in his own lifetime, redraw our map of the universe and reveal the hidden laws that govern everything, from the fall of an apple to the majestic dance of the planets. His name was Isaac Newton, and his story is not just one of scientific genius, but of profound human struggle and resilience. It's a testament to the idea that even from the deepest darkness, the most brilliant light can emerge. We often see figures like Newton as statues, carved in stone, remote and untouchable. But he was a man, born into a world of shadow and uncertainty, who found his light not in the company of others, but in the quiet solitude of his own relentless curiosity. He taught us that the universe is knowable, that its secrets are not beyond our grasp. So, come with me. Let's travel back in time to a small village in England, to a world lit only by fire and candlelight. Let's walk alongside this quiet, intense young man and witness how a mind, left to wander in the wilderness of its own thoughts, could unravel the very fabric of reality. This is the story of how one human being, armed with nothing but his intellect and an insatiable desire to understand, gave us the cosmos as we know it today. Our story begins not in a grand hall of learning, but in a modest farmhouse in Woolsthorpe, England, on Christmas Day, 1642. The world into which Isaac Newton was born was a fragile one. He arrived prematurely, a small and sickly infant, not expected to survive the day. His father, also named Isaac, had died 3 months before his birth, leaving him to a world without a father's embrace. This initial brush with mortality, this entry into a life already marked by loss, would cast a long shadow over the boy's formative years. He was a ghost in his own home before he could even walk. His mother, Hannah, remarried when Isaac was just 3 years old. Her new husband, a wealthy clergyman, had no desire to raise a stepson. And so, in an act that would wound him for the rest of his life, Isaac was left behind, entrusted to the care of his maternal grandmother. Imagine that. At an age when a child needs the warmth and security of a parent's love more than anything, he was abandoned. This profound sense of rejection, of being unwanted, became the bedrock of his young personality. He grew up in the shadow of the church his stepfather preached in, a constant looming reminder of the family he was not a part of. This solitude, however, became his sanctuary. While other children played games and forged friendships, Isaac turned inward. He found companionship not in people who had proven so unreliable, but in the world around him. He became a keen observer, his mind a silent sponge absorbing the details others overlooked. He watched the way the light filtered through the trees, the mechanics of a water wheel, the flight of a bird. His isolation wasn't empty. It was filled with questions. Why does the wind blow? How does the sun create a rainbow in a prism? The world became his classroom and his laboratory. In this crucible of loneliness, the seeds of his genius were sown. He didn't have the comforting stories or gentle guidance of a parent to explain the world. He had to figure it out for himself. This forced him to develop a powerful, independent mind, one that wasn't afraid to challenge accepted wisdom because for him, there was no wisdom to accept. He built things, intricate sundials, accurate to the minute, model windmills powered by a mouse on a treadmill, kites with lanterns attached, which he flew at night to the terror of the local villagers, who mistook them for comets. These weren't just the idle pastimes of a lonely boy. They were his first experiments, his first forays into understanding the physical principles that governed his world. He was, in essence, teaching himself the language of nature. The lack of human connection drove him to seek a deeper connection with the universe itself. The darkness of his childhood, the emotional void left by his family, became the fertile ground from which an unparalleled intellect would grow, destined to illuminate the world. When the time came for formal schooling, Isaac was sent to the King's School in Grantham. But the world of the classroom was no more welcoming than the world of his family. He was, by all accounts, a sober, silent, thinking lad, lost in his own world of diagrams and daydreams. He showed little interest in the rote memorization of Latin and Greek that formed the core of the curriculum. He was seen as strange, aloof, and worst of all, academically unremarkable. He was often at the bottom of his class, a fact that seemed to bother him little. His quiet, introspective nature made him an easy target. He was small for his age and preferred the company of his notebooks to the rough-and-tumble play of his classmates. This led to him being bullied relentlessly. The physical and verbal abuse was a constant reminder of his otherness. One day, the school bully, a boy who ranked just above him in class, delivered a particularly vicious kick to Isaac's stomach. Something in Newton snapped. It wasn't just the physical pain, it was the insult to his intelligence. The humiliation of being bested by someone he considered his intellectual inferior. This moment was a turning point. The quiet, passive boy vanished, replaced by a fierce, determined competitor. He challenged the bully to a fight after school, and, to everyone's surprise, the small, wiry Newton thrashed him soundly. But his victory wasn't complete. It wasn't enough to beat him physically, he had to crush him intellectually. From that day forward, Isaac dedicated himself to his studies with a ferocious intensity. He would not rest until he was not just better than the bully, but the top student in the entire school. His focus shifted entirely. The boy who once ignored his lessons now devoured them. He filled notebooks with meticulous notes, sketches, and complex mathematical problems that went far beyond the school's curriculum. He read voraciously, absorbing the works of Euclid and other classical thinkers. He built ever more complex contraptions, not just as toys, but as rigorous scientific instruments. He was no longer just observing the world. He was actively interrogating it, dissecting it, trying to understand its hidden machinery. This newfound passion for learning was all-consuming. He had tasted the power of his own mind and found it intoxicating. The approval of his teachers and the fear of his classmates meant little to him. What mattered was the pursuit of knowledge itself. He had discovered a universe within his own intellect, a place where he was not the strange, lonely boy, but a master, a creator. The pain of his past had been transmuted into an unquenchable intellectual fire that would soon set the entire world ablaze. In 1661, at the age of 19, Isaac Newton arrived at the hallowed gates of Trinity College, Cambridge. This was the world he had yearned for, a place dedicated to the life of the mind. Yet, even here, his path was not easy. He entered as a sizar, a type of work-study student. This meant he had to wait on tables, clean the rooms of wealthier students, and perform other menial tasks to pay for his tuition. He was, once again, an outsider, a servant in the temple of knowledge. But this time, he hardly noticed the social slights. He was surrounded by books. The Cambridge curriculum was still heavily rooted in the ancient teachings of Aristotle, a worldview that described a universe governed by purposes and essences, not mathematical laws. But a quiet revolution was stirring. The ideas of the new natural philosophy were filtering through the college walls. Thinkers like René Descartes, who saw the universe as a giant clockwork machine, and astronomers like Galileo Galilei and Johannes Kepler, who had mapped the heavens with mathematical precision, were challenging the old ways. Newton, with his innate distrust of received authority, was drawn to these radical new ideas like a moth to a flame. He began a second secret education. While his official studies followed the prescribed Aristotelian path, his private hours were spent devouring the works of these modern giants. He kept a special notebook he titled Questiones Quaedam Philosophicae, Certain Philosophical Questions. In it, he systematically challenged ancient assumptions about light, motion, and matter. He wasn't just reading. He was arguing with the greatest minds of his time, testing their ideas and pushing beyond them. He was building his own conceptual universe, brick by intellectual brick. His prodigious talent did not go unnoticed for long. The Lucasian professor of mathematics, a man named Isaac Barrow, recognized the startling genius in this quiet, intense student. Barrow was one of the few at Cambridge who truly understood the power of the new mathematics and physics. He took Newton under his wing, giving him advanced texts and encouraging his independent research. For the first time in his life, Newton had found a true mentor, someone who could see the brilliant light of his intellect and provide the fuel it needed to burn even brighter. But just as Newton was hitting his intellectual stride, fate intervened. In 1665, the Great Plague swept across England, a terrifying wave of death that emptied the cities. Cambridge University, like all public institutions, shut its doors, sending its students home to wait out the pestilence. Newton, now 22 years old, packed his books and his notebooks and returned to the isolation of the Woolsthorpe farmhouse. the world was plunged into fear and darkness. But for Isaac Newton, this forced retreat would become the most intellectually explosive period of his, or perhaps anyone's, life. Back in the solitude of Woolsthorpe, the world outside seemed to just, well, cease to exist for Newton. The fear of the plague, the shutdown of society, the silence of the countryside, it all just faded into the background. His mind, now freed from the constant distractions and duties of Cambridge, was truly unleashed. What followed was an annus mirabilis, a year of miracles. In the span of about 18 months, this young man, working entirely on his own, would lay the foundations for 3 brand new fields of science, and honestly, any one of those would have secured his place in history. His first conquest was mathematics. Newton was wrestling with problems of motion and change. How do you describe the path of a cannonball or the changing speed of a falling object? The mathematics of his day, which was based on static geometry, just wasn't up to the task. So, Newton invented a new one. He developed what he called the method of fluxions, which today we know as calculus. This was the mathematical language of change, a tool of breathtaking power that could describe the continuous flow of reality, from the infinitesimally small to the infinitely large. Next, he turned his attention to the nature of light. The prevailing theory, going all the way back to Aristotle, was that white light was pure and fundamental, and that colors were just a modification of it. Newton, though, was skeptical. In a darkened room, he allowed a single beam of sunlight to pass through a small hole and then through a glass prism. The result was the familiar rainbow of colors projected onto the opposite wall. But Newton didn't stop there. He took a second prism and, with almost surgical precision, used it to isolate a single color, say red, and pass it through the second prism. The red light stayed red. It didn't break down any further. This simple, elegant experiment proved that white light was not pure. It was actually a composite, a mixture of all the colors of the rainbow. The prism wasn't adding color to the light, it was just separating the colors that were already there. He then used a second inverted prism to recombine the spectrum back into a beam of pure white light, clinching his case. This discovery overturned 2,000 years of thinking and really laid the groundwork for the entire field of optics. It would eventually lead to the understanding of light as an electromagnetic wave. And finally, it was during this period of intense, isolated thought that the seeds of his greatest theory began to germinate. He sat in the garden at Woolsthorpe, his mind wrestling with the mysteries of the cosmos. He knew of Kepler's laws, which described the elliptical orbits of the planets around the sun, but they didn't explain why the planets moved that way. What force held them in their paths and prevented them from just flying off into the void? The answer, he began to suspect, was all around him, in the very ground beneath his feet. The miracle year was not some accident. It was the culmination of a lifetime of solitude, observation, and relentless questioning. It's perhaps the most famous anecdote in the entire history of science. Isaac Newton, sitting in the garden at his family home in Woolsthorpe, sees an apple fall from a tree. In that simple, everyday event, a whole universe of insight is revealed. Now, did it happen exactly like that? Was there a sudden eureka moment as the fruit bonked him on the head? Probably not. Newton himself told the story later in life, and he likely simplified it for effect. But the core of the story, the essential insight, is profoundly true and really reveals the unique character of his genius. Countless people for millennia had seen apples fall from trees. It was the most ordinary thing in the world. But only Newton asked the right question. He didn't just ask, why did the apple fall? The obvious answer was gravity. He asked, why does gravity pull the apple straight down to the center of the earth? Why doesn't it fall sideways or upwards? And then came the great leap of imagination, the flash of cosmic insight that bridged the terrestrial and the celestial. He wondered if the same force that pulled the apple to the ground might not also be the force that held the moon in its orbit around the earth. This was a revolutionary, almost heretical idea. For 2,000 years, since the time of Aristotle, the heavens and the earth were considered two completely separate realms, each governed by different sets of laws. The earth was the realm of imperfection, of decay, of straight-line motion downwards. The heavens were the realm of perfection, of eternal, unchanging circular motion. Newton's genius was to erase that line, to propose a single, universal law that applied to both apples and planets. He dared to imagine that the cosmos was unified. He began to perform a thought experiment. Imagine throwing the apple. It travels in an arc and hits the ground. Now throw it harder. It travels farther before it hits the ground. Now imagine you're on a very tall mountain, and you have a cannon that can fire the apple with incredible speed. If you fire it fast enough, as it falls towards the Earth's surface will curve away from it at the same rate. The apple would be constantly falling, but it would never get any closer to the ground. It would be in orbit. The moon, he reasoned, is just like that apple, forever falling towards the Earth. This was the conceptual breakthrough. The moon's orbit wasn't some perfect heavenly motion. It was the result of the same mundane force that made things fall. The force of gravity, he hypothesized, must extend far beyond the treetops, all the way out into the cosmos. He still had to do the hard mathematical work to prove it, to show that this force weakened with the square of the distance. But the idea, the beautiful, unifying, universe-altering idea, was born there, in a quiet garden, inspired by the simple fall of an apple. For nearly 20 years after his miracle year, Newton's most profound discoveries remained, well, largely hidden from the world. He was secretive, almost pathologically averse to criticism, and focused on other pursuits, including alchemy. His work on gravity was a set of scattered notes, a brilliant but unfinished symphony. The world might never have known of it if not for a visit in 1684 from the astronomer Edmund Halley, the man for whom the famous comet is named. Halley was vexed by the same problem as everyone else. What law of force would produce the elliptical orbits of the planets described by Kepler? Halley posed the question to Newton during a visit to Cambridge. Newton replied, almost nonchalantly, that he had calculated it long ago, and the answer was an inverse square law. The force diminishes by the square of the distance between the objects. Stunned, Halley asked to see the calculations. Newton, unable to find his original notes, promised to rederive them and send them along. What he sent a few months later was a 9-page treatise that was so much more than a simple proof. It was the seed of a complete system of the world. Halley, recognizing its monumental importance, knew it had to be published. Urged on by Halley, and with Halley generously footing the bill for publication, Newton embarked on a period of intense, almost superhuman labor. For 18 months he barely ate or slept, completely consumed by the task of writing his masterpiece. He was a man possessed, driven to articulate the complete mathematical framework of the universe as he now understood it. The result, published in 1687, was the Philosophiae Naturalis Principia Mathematica, or the Mathematical Principles of Natural Philosophy. It is, without exaggeration, the single most important scientific book ever written. The Principia did not just propose the law of universal gravitation. It laid out a complete methodology for doing science. It began with definitions of mass, momentum, and force. It then presented his 3 famous laws of motion. An object in motion stays in motion. Force equals mass times acceleration. And for every action, there is an equal and opposite reaction. These laws form the bedrock of mechanics, the fundamental rules of how everything in the universe moves. They were simple, elegant, and universal. From these simple axioms, Newton used his powerful calculus to derive not only Kepler's laws of planetary motion, but also the behavior of tides, the trajectories of comets, the precession of the equinoxes, and the slight bulge of the Earth at its equator. It was a breathtaking display of intellectual power. He had taken the messy, complicated universe and shown that it operated according to a few simple, precise mathematical laws. He had given humanity the user's manual for the cosmos. The world was no longer a place of mysterious, divine whims. It was a rational, predictable, clockwork universe, and Isaac Newton had just handed us the key. The publication of the Principia made Newton the most celebrated scientist in Europe, but it did not bring him peace. His personality, solitary, suspicious, and fiercely protective of his work, made conflict almost inevitable. He was a man who could divine the laws of the cosmos, but struggled mightily with the laws of human interaction. His career was marked by a series of bitter, acrimonious disputes with his scientific rivals, conflicts that consumed his energy and revealed a darker, more vindictive side to his genius. His longest and most bitter feud was with Robert Hooke. Hooke was a brilliant and versatile scientist in his own right, the curator of experiments for the Royal Society. He was a man of 1,000 ideas, but he often lacked the mathematical rigor to fully develop them. Hooke had corresponded with Newton about planetary motion and claimed that he had given Newton the key idea of the inverse square law. When the Principia was published with no mention of Hooke's contribution, Hooke was, understandably, enraged and accused Newton of plagiarism. Newton reacted with volcanic fury. He denied Hooke's claim vehemently, arguing that others had suggested the inverse square law as well, but only he, Newton, had possessed the mathematical power to prove it and derive all its consequences. The dispute became intensely personal. Newton went through the manuscript of the Principia and systematically removed nearly every reference to Hooke. He developed a deep and abiding hatred for the man, a hatred that would last until Hooke's death. It was a clash not just of ideas, but of personalities. Hooke, the sociable, intuitive experimentalist, versus Newton, the solitary, rigorous mathematician. An even more famous and consequential dispute erupted over the invention of calculus. While Newton had developed his method of fluxions during his miracle year in the 1660s, he had kept it largely to himself. In the meantime, on the European continent, the brilliant German philosopher and mathematician Gottfried Wilhelm Leibniz had independently developed his own, remarkably similar system of calculus. Leibniz published his work first, in 1684, and his notation, the elegant dx over dt and integral signs we still use today, was far superior to Newton's clumsy dot age. When Newton's supporters claimed that Leibniz had stolen the idea from Newton's unpublished papers, a vicious, nationalistic priority dispute broke out. It pitted the English scientific establishment against their continental counterparts. Newton, using his powerful position as president of the Royal Society, orchestrated a supposedly impartial committee to investigate the matter. In reality, he secretly wrote the committee's final report himself, which shamelessly accused Leibniz of plagiarism and fraud. The conflict was a stain on the legacies of both great men and set back the progress of British mathematics for nearly a century as they stubbornly clung to Newton's inferior notation. These battles show that even a mind that could encompass the universe was still susceptible to the very human flaws of pride, insecurity, and vanity. In the years following the Principia, Newton's life transformed. He moved from the quiet cloisters of Cambridge to the bustling political and social world of London. In 1696, he was appointed Warden of the Royal Mint, and later, Master of the Mint. This was no mere honorary position. The English currency was in crisis, riddled with counterfeit and clipped coins. Newton threw himself into the job with the same ferocious intensity he had applied to science. He became a brilliant administrator and a relentless detective, personally hunting down and prosecuting counterfeiters, some of whom he sent to the gallows. This new role gave him power, wealth, and influence. He was no longer the poor sizar or the reclusive scholar. He was a major figure in the British establishment. In 1703, his old adversary Robert Hooke died, and Newton, as if waiting for the opportunity, immediately accepted the presidency of the Royal Society, the most prestigious scientific body in England. He would rule over the society like an absolute monarch for the next 24 years until his own death. His leadership was transformative, but also authoritarian. He used his position to promote his own work and that of his followers, creating a scientific orthodoxy centered on his own theories of gravity and light. He brooked no dissent. His control was so absolute that he allegedly had the official portrait of Robert Hooke removed and destroyed, an act of posthumous vengeance. He settled old scores and used the power of the institution to wage his war against Leibniz, solidifying his claim to the invention of calculus in the eyes of the British scientific world. In 1705, Queen Anne visited Cambridge and, in a grand ceremony, bestowed a knighthood upon him. He was now Sir Isaac Newton. It was the first time a scientist in England had been honored in this way, a powerful symbol of the rising status of science in the Age of Enlightenment. He had become more than a scientist. He was a national icon, the living embodiment of British intellectual prowess. His image was carefully curated, the wise, silver-haired patriarch of reason, whose genius had revealed God's divine plan for the universe. Under his leadership, British science flourished, but it also became somewhat insular, cut off from the vibrant mathematical developments happening on the continent due to the calculus dispute. Newton became the ultimate authority, the final arbiter of scientific truth. His word was law. He had journeyed from being a complete outsider, a fatherless, friendless boy, to becoming the unchallenged ruler of the scientific world. He had built the temple of modern science, and now he sat upon its throne. As he grew older, Sir Isaac Newton dedicated less of his time to what we would now call science and more to other, more esoteric passions. It's a part of his life that is often overlooked, but it is essential to understanding the whole man. Newton did not see a firm line between his study of the physical world and his study of theology and alchemy. To him, it was all part of the same grand quest to understand the mind of God. He spent countless hours and wrote over 1 million words on these subjects. He delved deeply into biblical chronology, attempting to use astronomical records and ancient texts to calculate the precise date of creation and to prophesize the date of the apocalypse. He believed the Bible was a book of prophecy written in a divine code, and if he could just apply the same rigorous logic he used on the cosmos, he could unlock its secrets. He held unorthodox religious beliefs, secretly rejecting the doctrine of the Trinity, a heresy that could have destroyed his career had it become public knowledge. He saw the universe as a temple, and its creator as a master mathematician. His alchemical pursuits were equally intense. This wasn't the foolish quest for turning lead into gold for riches. For Newton, alchemy was a serious, experimental investigation into the hidden properties of matter. He believed that matter was composed of active living principles, and through fire and chemical manipulation, he hoped to uncover the fundamental secrets of its transformation. He was searching for the philosopher's stone, not for wealth, but for wisdom, for a deeper understanding of God's creative power in the material world. These pursuits, which might seem unscientific to us, were central to Newton's worldview. He never believed that his mechanical universe ran on its own. He saw gravity not as an inherent property of matter, but as the direct and continuous action of God's will, a divine force actively holding the cosmos together at every moment. His science was not a replacement for God, it was a testament to God's power, intelligence, and majesty. The clockwork universe needed a clockmaker. In his final years, he was a revered and honored figure, a living legend. He lived comfortably in London, surrounded by his disciples, his niece Catherine Barton acting as his hostess. When he died in his sleep in 1727 at the age of 84, he was given what amounted to a state funeral. His body lay in state in Westminster Abbey, and his coffin was carried by dukes and earls. He was buried among the kings and queens of England, a testament to the profound impact he had on his nation and on the world. The solitary boy from Woolsthorpe had found his final home among royalty. I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me. These are Newton's own words, a humble reflection from a man who had seen farther than any human before him. He had not just found a few pretty shells, he had given us the tools to navigate that great ocean of truth. His legacy is all around us. The laws of motion and universal gravitation that he laid down in the Principia governed the field of physics for more than 200 years. They made possible the Industrial Revolution. They allowed us to predict the return of comets, to discover new planets based on their gravitational pull on others, and eventually, to launch spacecraft that would travel to the moon and beyond. Every time an engineer designs a bridge, an architect calculates the stress on a building, or a satellite is placed in orbit, they are using the principles that Newton first articulated. His work in optics fundamentally changed our understanding of light and color, paving the way for modern telescopes, cameras, and the entire science of spectroscopy, which allows us to know what distant stars are made of. His invention of calculus gave us the mathematical language to describe the changing world, a tool now indispensable in fields as diverse as economics, biology, and computer science. He established a new paradigm for science itself, a combination of rigorous experimentation, mathematical modeling, and the search for universal laws. But perhaps his greatest legacy was a philosophical one. Newton demonstrated that the universe was not a chaotic, incomprehensible mystery, but a rational and ordered place governed by laws that human reason could discover. He empowered humanity. He showed us that we were not merely passive observers of the cosmic drama, but that we could understand the script. This idea, that the universe is knowable, is the very foundation of the modern scientific enterprise and the spirit of the Enlightenment. Albert Einstein, whose theory of relativity would eventually supersede Newtonian physics in the realms of the very fast and the very massive, kept a portrait of Newton on his study wall. Einstein didn't see himself as overturning Newton, but as building upon the foundation he had laid. As Newton himself famously said, "If I have seen further, it is by standing on the shoulders of giants." For 3 centuries now, all of science has, in one way or another, stood on the shoulders of that solitary, brilliant, and difficult man, Isaac Newton. He remains the ultimate giant. The story of Isaac Newton is a powerful reminder that the greatest revolutions often begin in the quietest of places. They start not in the halls of power, but in the curious mind of a single individual who dares to look at the ordinary world and ask extraordinary questions. Newton's journey from a lonely, overlooked boy to the architect of our modern understanding of the universe is a testament to the boundless potential that lies within the human intellect. He took a world of superstition and mystery and gave us a cosmos of order and elegance. His life teaches us that solitude can be a crucible for genius, that adversity can be forged into determination, and that a relentless pursuit of truth can, quite literally, change the world. He showed us that the same laws that govern the simple fall of an apple also choreograph the grand ballet of the planets. This profound unity, this cosmic connection, is his most enduring gift to us. It allows us to look up at the moon and see not a distant, alien object, but a fellow traveler, bound by the same invisible force that holds us to the earth. So the next time you gaze up at the stars, think of the quiet boy from Woolsthorpe. Remember that the universe is not only stranger and more wonderful than we imagine, it is more understandable than we might think. The quest for knowledge that Newton began is far from over. That great ocean of truth still stretches out before us, vast and deep, waiting for the next generation of explorers to step onto the shore, to pick up a stone, and to wonder. The journey continues, and it's a journey for all of us.